Geometric probability.
Right. In today's notes, we're going to talk about geometric probability. As the title would suggest, this is a type of probability that is very closely related to geometry. In particular, it's going to be related to, most of the time, it's going to be related to the concept of area. All right, here's what it is. Geometric probability is used when points on a segment or a region are outcomes. Okay, what we have as either a segment or as a region is you have a limited amount of space. And on that space, there's all kinds of different locations that you can choose. And what we're going to look at is what would be the probability of choosing a particular location versus all the locations that are in that region or on that segment. Example number 1 says, if a point K is on ST, so we have a line segment here that goes all the way from S to T, that's also 2 to 14. If point K is on ST and is chosen at random, we just randomly grab a point there, what is the probability that K lies on QR? Okay, so we've got all the way from here to here available, which is a total of 12 units. You can get that by taking the 14 minus 2. So you have a total of 12 units available. What would be the probability that K ends up between Q and R? Well, Q to R, let me write that a little bit better for you there. Q to R has a length of 3 units. So our probability, and this is like theoretical probability, just to tie back to the last set of notes, is going to be 3 out of 12. Right, there's 3 segments out of a total of 12 segments that are part of our favorable outcomes. That does reduce down to 1/4, which you can also call 25% or 0.25. Again, how you answer that is kind of optional right now, but definitely if you can reduce it, at least do that much of it. If you do recognize it as a nice percentage, that's a good way to answer the question as well. Example number 2 is going to be our example that refers to area and choosing points that would be within a space. So not sitting on a segment, but within a space. What we have is a picture of a circle that is inscribed into a square, and the side length of the square is 6, which means, of course, the diameter of the circle is going to be 6 as well. Question, what is the probability that a point is chosen at random and it lies in a shaded region? Now, I don't know if you can quite see all the shaded region parts, but that's going to be all these weird little corners that sit between the circle and the square. Okay, so all possible outcomes, the denominator spot of our probability is going to be the square. It's going to be the square part. Okay, your favorable outcomes are going to be all of these shaded regions. Now, the way that we get the shaded regions is we take the square and we subtract the circle. Okay, so you might remember that part from some previous stuff when we studied area and finding these unusual shaded regions. We usually take a larger figure and we just remove the pieces that we don't want. So we'll still do that, but in addition to it, we will just divide it by the total area, which was that square again. All right, so the square is a 6 by 6, so we can go ahead and just do that math. That's 36. All right, the circle is going to be, for the area of the circle, it's pi r squared. All right, the diameter is going to be 6, which means that your radius, let's add that to the picture, your radius is a 3. So we're going to take the area of 36, we're going to subtract pi 3 squared, which is the same thing as 9 pi. We'll then divide that by 36. Now, in this problem, because we have the pi in there, this will be one of those cases where, well, let me think about it here. In the past, when we just did general calculations of volumes or areas, sometimes we leave them in terms of pi. But because that is the only part that's in terms of pi versus the other stuff, I'm going to go ahead and just evaluate the whole thing and then present this answer strictly as a percentage. All right, so we got 36. We're going to subtract 9 pi. which of course is going to give you some unusual decimal number. We then divide that by 36, and this is our probability, which is going to be about, let's do 21.5. We'll round that last number up. So I'll say that it is 21.5%. All right, when you're done with these questions, you should always give it a little look here just to see if it sort of makes sense. This is about a fifth. 20% is about a fifth. Well, 20% is a fifth of an area. So this is approximately a fifth of the area of the square, and it might add up. Well, I mean, it looks like it could be there. It's about that much once you add all the pieces together for that. All right, let's take a look at example number 3. Look at that picture. All right, it looks like we have some sort of a target, and it says that there we have an archery target. And we have a bunch of different rings on here. It has different colors that go along with them. The original problem that I found was colored, so the whole thing here is going to be in black and white. And hopefully that I marked this spot will kind of clarify what we're looking for here. All right, let's see what we got. The inner circle is going to have a radius, just a radius right here of 1.22 centimeters for that part. The width of every ring is also going to be 1.22 centimeters. So that same length there is what you're going to get between like these rings, or the width of that ring. And then you're also going to have 1.22 here, 1.22, 1.22 as well. All right, question, what is the probability an arrow hits the smallest ring? So that's why I put the X there, so you knew which one I was going to refer to with that. All right, before I begin working out the problem, what I would suggest that you do is pause the video and see if you can set up some sort of a, an outline to what we want. Now, things that are gonna be like in the last problem, you are gonna have a fraction. The bottom of that fraction, that denominator, is gonna be the total area. That's a given, okay? It's gotta be the entire circle. The part that's going to be a little bit challenging is to figure out what is the area of that particular ring and getting that calculation right there. All right, so give that a shot and see if you get the same thing I do. All right, what I have here is not a complete solution, as you can tell, but what I did do is I wrote down some key values that I'm going to need to set up the whole problem, okay? And I figured I would at least do that part before, so you don't have to watch me add it all. But here's what they are. So these are all radius, and I just put little subscripts to refer to different areas that are here. So the radius of the total thing, so the biggest one, and we talked about that needing, like you need to find the total area anyway as a denominator. So the radius of the total thing is going to be 1, 2, 3, 4, 5 multiplied by 1.22. Right? And you add them all up, it's just 5 times that. So the radius of the largest circle is 6.1. All right, then getting closer to what we want, the radius of the ring that we're going to be concerned with, like if it was a full circle here, is going to be 2 times 1.22, because you have the 1.22 here and then another 1.22 for that part. All right, in addition to that, I have one more, which is going to be the radius of the inside circle that we already knew, but I wanted to write it down, and I'll call that one R1. That has a radius of 1.22. Okay, so for the denominator, we look at the total area of the figure, which is going to be pi times the total radius squared, which is the 6.1. Okay, so that's your total area. All right, for the top, we want to be within this ring here, but not in that spot. So what I'm actually going to start with is figuring out what would be the area of this ring, as if that wasn't taken out, that little dark circle in the middle was not removed. So that would be pi times 2.44 squared. Okay, so if I just set this up, and I ran those calculations, this would give me the probability that I end up within that ring of the whole thing. But I don't want to just be within that ring. I want to also make sure that I'm outside of the ring that's in the dead center. So I'm going to take that area away from this area. So we're going to be subtracting on the top pi 1.22 squared. Okay, and all together, that should get us to our probability. Now, something neat about this example that I wasn't able to do in the last one. Every term that we have, this is a term, this is a term, and this is a term. Every term that we do have involves the pi symbol. All right, so if that's true, you can actually take them out. Now, if you don't trust that as the math, you can do it with the pi symbol and it's fine. You'll get an answer. It's going to be the exact same thing that I do. But you could take that out. So that'll give you 2.44 squared minus 1.22 squared divided by 6.1 squared. All right, and then from there, I don't really have any tricks. Here's what you can't do, just to be clear. I know I just showed you, hey, look, you can take a pi from all of these. And you can do that because it's a factor. Here's what you can't do. You can't just take all the squareds from there. So you got to keep those in when you move into this next part. All right, so from here, you really just type it in. That's all it is. 2.44 squared. We're going to subtract 1.22 squared. Okay, and that is going to represent our numerator. That is our favorable area, that white ring. We'll divide that by 6.1 squared. And we end up with that number, which actually turns out to look pretty nice. So we get 0.12, but as a percentage, that is going to be 12%. And then when you're all done with it, you take a look at it and you see if that sounds reasonable, right? 100% is the entire thing. What we have here is this ring, and we're describing it as 12% out of that 100, and that sounds like a fair amount that we're getting for that answer.